Imagine you are a scientist. You've spent years designing an experiment. You've written the proposals, survived the review committees, and finally convinced the most powerful space telescope ever built to point its golden eye at something only 26,000 light years away. Something that has been staring back at us since long before our species existed. The plan is simple. Watch it. Take notes. You expect to see what every textbook says you'll see. A relatively quiet, intermittently flickering object. A sleeping giant. A black hole that, by all accounts, barely eats anymore. What you get instead is something that, in the words of the lead scientist on the project, is new and exciting every single time we look at it. Not once, not twice, every single time. Then the data tells you something stranger still. Every day this object explodes, not metaphorically. 5 to 6 massive eruptions of energy, every single day, plus dozens of smaller ones in between, with no pattern, no rhythm, no warning, no explanation. And then, buried in the fine structure of the light curves, your instruments reveal something that has never been seen before at these wavelengths. A time delay, a shift, one color of light arriving a few seconds before another from the same event at the same source, happening in the same fraction of a second near the edge of a black hole. And you realize, we have been watching this object for decades. We thought we understood it. We gave it a name. We photographed its shadow. A Nobel Prize was awarded for the work done here. And it is only now, with the sharpest eyes humanity has ever put in space, that we are starting to understand how little we actually knew. This is the story of Sagittarius A star, the black hole at the heart of the Milky Way, and what the James Webb Space Telescope saw when it watched it, day after day, for an entire year. I'm Mo, and you're watching NullaraX. Let's start with what this thing actually is. Right now, as you watch this, as you breathe, as your heart beats, there is a black hole at the center of your galaxy. It sits approximately 26,000 light years from Earth in the direction of the constellation Sagittarius, and it is, by almost any measure, incomprehensibly large. Its name is Sagittarius A star, and it contains the mass of approximately 4 million suns. 4 million? Pack the mass of 4 million stars, each like our own, into a region of space roughly 14 to 15 million miles across. That sounds vast until you remember that the distance from Earth to the Sun is 93 million miles. Sagittarius A star, the entire black hole, would fit comfortably inside the orbit of Mercury. Now hold that thought, 4 million solar masses, compressed into something smaller than Mercury's orbit, and at the center of it all, a singularity. A point where the known laws of physics simply stop working. The boundary of this object, the point of no return, the event horizon, is called the Schwarzschild radius. Cross it, and even light cannot escape. Not because anything is pulling light back, but because space-time itself curves so sharply that all paths forward lead inward. You wouldn't be falling toward the center. Inward would be the only direction time has left. But here's something almost no one tells you. From the outside, a black hole like Sagittarius A star is not dark. Far from it. The material falling toward it, gas, dust, shredded clouds of hydrogen, the occasional asteroid, stellar winds from nearby massive stars, all of it forms what astronomers call an accretion disk, a vast swirling structure of superheated plasma orbiting the black hole at significant fractions of the speed of light. Temperatures in this disk can reach tens of billions of degrees. It glows in X-rays, in radio waves, in infrared light, in a way that no star ever could, because no star is being compressed and heated by the gravity of something 4 million times the mass of the Sun. Sagittarius, A star, is not a darkness in the sky. It is, when it wants to be, the brightest thing in the galaxy. The question that Webb set out to answer was deceptively simple. What is it doing right now? The story of how we came to know this object at all is one of the great detective stories in the history of science. It begins in 1928 at Bell Laboratories in New Jersey, where a young engineer named Karl Jansky was hired to do a very unglamorous job. Jansky was assigned to find the source of radio static that was interfering with transatlantic telephone transmissions. He built a large rotating antenna, colleagues called it Jansky's merry-go-round, and he pointed it at the sky, systematically sweeping through the directions where noise was strongest. What he found, published in 1933, was that the strongest and most persistent radio signal was coming not from any thunderstorm, not from the sun, but from a fixed point in the constellation Sagittarius, from the center of the galaxy. The New York Times ran the story on May 5th, 1933, under the headline, "New Radio Waves Traced to Center of the Milky Way." Jansky had accidentally detected the galactic center, the most extreme environment in our cosmic neighborhood. He didn't live to understand what he had found. Decades passed. In 1974, two radio astronomers at the National Radio Astronomy Observatory, Robert Brown and Bruce Balick, discovered a point-light, unusually intense radio source within the region Jansky had identified. Something small, something dense, something radiating far more power than its surroundings. Brown named it Sagittarius A star, using the asterisk to denote that the source was excited, a notation borrowed from atomic physics. The name stuck. But what the thing actually was remained controversial. The leading hypothesis, that it was a supermassive black hole, had a serious problem. You cannot take a picture of a black hole directly. By definition, it emits no light. You can only infer its presence from the behavior of everything around it. And in the 1990s, two groups of astronomers decided to do exactly that, working independently. One team in Europe, led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics. The other in California, led by Andrea Ghez at UCLA. They both had the same audacious idea. Point the best infrared telescopes on Earth at the galactic center and track the stars orbiting whatever was there. It took years. Stars moved slowly enough that a decade of observations was needed to trace even a partial arc. But as the years accumulated, the orbits came into focus, and the orbits were extraordinary. One star in particular, catalogued as S2, was moving faster than any star had ever been observed to move around any gravitational source. At its closest approach to Sagittarius, A star, it reached speeds of approximately 7,600 kilometers per second. That is about 2.5% of the speed of light. A star moving at 2.5% the speed of light around an invisible point of gravity, applying Kepler's laws, the same laws that govern planets orbiting the Sun, derived by Johannes Kepler in the early 17th century. Both teams calculated the mass of the unseen object. The answer from both groups was the same. Roughly 4 million solar masses confined within a volume smaller than the distance light travels in a matter of hours. There was no known object in physics other than a black hole that could produce this result. In 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for this work, for turning a radio anomaly first spotted by an engineer looking for telephone static into the most precisely documented black hole in the universe. But knowing a thing exists is not the same as understanding it. And understanding Sagittarius A star, really understanding what it does, how it behaves, what drives its violence, required something that no ground-based telescope, no matter how powerful, could provide. It required a telescope above the atmosphere, a telescope cold enough to see in infrared, a telescope with a mirror the size of a tennis court. It required Webb. The James Webb Space Telescope launched on December 25, 2021 from the Guiana Space Center in Kourou, French Guiana. It traveled to its operating position, a gravitationally stable point called L2, approximately 1.5 million kilometers from Earth. And over the following months, deployed its gold-plated beryllium mirror, cooled its instruments to within a few degrees of absolute zero, and opened its eyes for the first time. The first public images from Webb, released in July of 2022, were a cultural moment. Fields of galaxies at distances so vast that the light had travelled for over 13 billion years. A stellar nursery in the Carina Nebula, rendered in a detail that made previous images look like sketches. The atmospheric spectrum of an exoplanet, with carbon dioxide clearly detected for the first time. Webb was everything it promised to be, and then some. But the galactic centre had its own challenges. Sagittarius A star sits behind a thick curtain of interstellar gas and dust, so thick that optical telescopes see almost nothing. The galactic centre is effectively invisible to human eyes. This is why, despite being the closest supermassive black hole to Earth, it took so long to understand. You could not simply point a telescope at it and look. Webb, however, sees in infrared. Infrared light, experienced by us as heat, passes through dust clouds that block optical wavelengths entirely. For Webb, that curtain of gas and dust between us and the galactic centre becomes nearly transparent. And in 2022, just months after Webb became operational, the Event Horizon Telescope, a global network of radio telescopes linked together to function as an Earth-sized dish, released something remarkable. The first direct image of Sagittarius A star itself, a blurred orange ring of hot plasma surrounding a dark central shadow roughly the size of the event horizon. It was the first time humanity had seen it, not inferred it, not calculated it, seen it. But the image was static, an average, a composite. It could not show what the black hole was doing from moment to moment, because radio telescopes cannot image fast enough to capture the rapid variations in brightness that occur near the event horizon. That is where Webb's infrared cameras come in. And so in 2023, a team of astrophysicists led by Farhad Youssefzadeh at Northwestern University began what would become the most detailed, sustained observation of Sagittarius A star ever attempted. They had a plan, they had a hypothesis. What they did not have was any idea what they were about to find. The team's instrument of choice was Webb's NullaraX, the near-infrared camera, which has a unique capability that proved critical to everything that followed. NullaraX can observe two separate wavelengths of infrared light simultaneously. In the case of these observations, the team chose 2.1 microns and 4.8 microns. These are wavelengths in the near to mid-infrared range, invisible to human eyes, but faithfully recorded by Webb's detectors. Observing both at once was, as Youssefzadeh described it, like seeing in colour instead of black and white. You don't just know the brightness, you know how the brightness varies between two different colours of light at precisely the same moment. Over the course of 2023 and 2024, the team pointed Webb at the galactic centre across 7 separate observing sessions, each lasting between 8 and 10 hours. The total observing time accumulated to approximately 48 hours, 2 full days of uninterrupted watching spread over a full year. They expected to see flares. Sagittarius A star had been known to produce infrared flares since the early 2000s, detected by ground-based telescopes. Occasional dramatic brightenings that would appear, peak, and fade over the course of minutes to an hour. The existing picture was one of an object that occasionally erupted, but that also had long quiet stretches in between. A sleeping dragon, waking up now and then drifting back to sleep. That picture was wrong. When the data came in, Youssefzadeh's team encountered something they had not anticipated. There were no quiet periods. None. In our data, we saw constantly changing, bubbling brightness, Youssefzadeh said. And then, boom, a big burst of brightness suddenly popped up. Then it calmed down again. But calm down is relative. Between the big bursts, the data showed continuous low-level flickering. The black hole was never still. In every single observing epoch, every 8 to 10 hour window, across 48 total hours, across the span of a full year, Sagittarius, a star, was producing variability. Not just once or twice, continuously, endlessly. The team counted the major flares, on average 5 to 6 per day. In addition to those, numerous smaller subflares in between, and beneath even those, detectable only because Webb's sensitivity is extraordinary, a constant seething background of flickering on timescales of mere seconds. We couldn't find a pattern in this activity, Youssef Zada said. It appears to be random. The activity profile of this black hole was new and exciting every time that we looked at it. Think about what that means for a moment. This is not a distant quasar in some far galaxy. This is our own galactic center, the object around which our entire Milky Way, every star you've ever seen in the night sky, every nebula in every astronomy photograph, slowly revolves. It is the gravitational anchor of our entire cosmic home. And it is, apparently, in a constant state of violent upheaval. 5 to 6 major explosions every day. And we never knew, because we never watched it this closely, this continuously before. But there was more. The truly strange part was still coming. As Youssef Zada's team dug deeper into the data, they noticed something that began to resolve the chaos into structure. The variability wasn't all one thing. When they plotted the brightness of the flares, categorized by how bright they were and how long they lasted, a pattern emerged. Not in the timing of the flares, which remained stubbornly unpredictable, but in their physical character. The faint, brief flickers behaved differently from the large, dramatic eruptions, not just in degree, in kind. The team concluded that 2 separate physical processes were responsible. Think of it this way. Imagine Sagittarius A star's accretion disk as a river. The faint, rapid flickers, lasting only seconds, are like small ripples on the river's surface. They arise from turbulent fluctuations within the plasma of the disk itself. In this model, the charged particles in the disk, electrons and ions moving at tremendous speeds, are constantly being jostled and compressed by the turbulence inherent in a disk of superheated gas orbiting a black hole. When this turbulence momentarily compresses a pocket of plasma, the electrons in that pocket briefly radiate more intensely. A flicker appears in the light curve. It lasts seconds, then disappears as the plasma expands and cools. This is analogous, the team noted, to how the sun's magnetic field can gather, compress, and then erupt in a solar flare. Except around Sagittarius A star, the magnetic fields are vastly more powerful. The temperatures are incomparably higher, and the timescales are measured not in hours but in fractions of a minute. The larger flares, 5 to 6 per day, brilliant and sustained, are something else entirely. These are tidal waves, not ripples. The leading explanation for these bigger events is a process called magnetic reconnection. Picture 2 magnetic field lines in the accretion disk, tangled together, straining against each other like drawn rubber bands. Eventually, the tension becomes unsustainable. The field lines snap, reconnect in a new configuration, and release a tremendous burst of energy in the process. The particles near the reconnection point are accelerated to close to the speed of light. These relativistic electrons spiral along the now reconnected field lines and emit intense radiation, a flare that Webb can detect across 26,000 light-years of space. In the team's paper, published in the Astrophysical Journal Letters on February 18, 2025, they described this as evidence for distinct populations of faint and bright variable emission. 2 different physical regimes operating simultaneously in the same compact region around the same black hole, and both are happening all the time without ceasing. But even this was not the most surprising finding. because NullaraX was recording two colors of light simultaneously, 2.1 microns and 4.8 microns. The team could do something that no previous observation of Sagittarius A star had been able to do. They could compare the exact timing of the same event at two different wavelengths. What they found when they ran this analysis has been called in the paper itself a first. Something never seen before in observations of this object at these wavelengths. A time delay. When a flare brightened at 2.1 microns, the 4.8 micron emission did not brighten at exactly the same moment. It lagged behind by between 3 and 40 seconds. This is the first time we have seen a time delay in measurements at these wavelengths, Youssef Zadeh said. We observed these wavelengths simultaneously with NullaraX and noticed the longer wavelength lags behind the shorter one by a very small amount, maybe a few seconds to 40 seconds. Now, 40 seconds sounds trivial, and in everyday terms, it is. But remember where we are. This is happening within the innermost few light minutes of a black hole's gravitational environment. The event horizon of Sagittarius A star has a radius of approximately 12 million kilometers. Light takes roughly 40 seconds to cross that distance. The time delay we are detecting is physically happening in a region the size of the black hole's own gravitational boundary. We are watching physics occur at the event horizon in real time. The physics behind the delay is this. The electrons emitting this radiation are not at rest. They are spiraling at relativistic speeds around magnetic field lines. As they spiral, they radiate. But a high-energy electron does not radiate at all wavelengths equally. It emits predominantly at shorter wavelengths first. Then, as it loses energy by radiating and begins to slow, its emissions shift toward longer wavelengths. This is called synchrotron cooling, and it means that when a burst of newly energized electrons lights up in the accretion disk, their 2.1 micron emissions peak slightly before their 4.8 micron emission. The shorter wavelength peak comes first. The longer wavelength peak follows, seconds to tens of seconds later, as the electrons cool. By measuring this time delay, the team could for the first time directly estimate the magnetic field strength in the immediate environment of the black hole. Their analysis yielded a magnetic field between 40 and 90 Gauss, extraordinarily powerful by any standard. For context, Earth's surface magnetic field is approximately 0.5 Gauss. The magnetic field threading the accretion disk of Sagittarius A star is between 80 and 180 times stronger. This is the environment we are watching erupt 5 to 6 times every day. A superheated plasma bath with magnetic fields 100 times stronger than Earth's, orbiting a 4 million solar mass singularity at a significant fraction of the speed of light. And the light from all of it reaches us 26,000 light years away, changed and encoded with the story of exactly what happened. To understand why these findings were surprising, you have to understand the previous model of what Sagittarius A star should be. Black holes are not all alike. At the far end of the spectrum, the violently active end, are what astronomers call active galactic nuclei, or AGN. These are supermassive black holes in the centers of distant galaxies that are consuming enormous quantities of material. Their accretion disks glow so brightly that they outshine the entire rest of the galaxy. Some of them produce relativistic jets, beams of plasma fired out along the rotational axis of the black hole at close to the speed of light, extending for hundreds of thousands of light years. These objects are among the most powerful in the universe. Sagittarius A star is not one of them, not even close. Sagittarius A star is what astrophysicists call a low luminosity active galactic nucleus, or LLAGN. Its accretion rate is extraordinarily low. The amount of material falling into it is a tiny fraction, less than a fraction of a percent, of what would be needed to power the kind of activity we see in distant quasars. By the standards of the observable universe, our galaxy's central black hole is essentially starving. This low accretion rate led to a theoretical expectation that Sagittarius A star would be relatively quiet and predictable. Yes, it flares, that was known, but the existing observations taken with ground-based infrared telescopes in limited observing windows painted a picture of an object with long, quiet baselines interrupted by occasional eruptions. The implicit assumption was that what you saw in a 2-hour observing window was representative of the broader behavior. If it was quiet during your 2 hours, it was probably quiet most of the time. Webb showed that assumption was wrong at a fundamental level. It is always bubbling with activity and never seems to reach a steady state, Yousefzadeh wrote. And that word, never, carries enormous weight. The accretion physics models that currently exist for low luminosity AGN, like Sagittarius A star, do predict variability, but they do not predict the level of continuous non-stop activity that Webb has now documented. The degree of variability, its persistence, and especially the fact that it appears to be truly random, no periodicity, no pattern the team could detect, are all pushing against the edges of existing models. Sagittarius A star is behaving like something we do not fully have a model for, and it has been doing so, presumably for as long as it has existed. We simply did not have an instrument sensitive enough to see it clearly until now. There is a second discovery from this era of Webb observations that deserves its own moment. While Yousefzadeh's team was conducting their NearCam survey, a separate international team, led by researchers at the Max Planck Institute for Radio Astronomy in Germany, including scientist Gunther Witzel, was pursuing a complementary goal. They wanted to observe Sagittarius A star with Webb's MIRI instrument. MIRI stands for the Mid-Infrared Instrument, and it observes at longer wavelengths than NearCam. Its sensitivity extends into the thermal infrared, the part of the spectrum where objects glow not because they are hot enough to emit visible light, but because they have any heat at all. On April 6, 2024, MIRI detected something from Sagittarius A star that had never been detected before, a mid-infrared flare. This is not a subtle distinction. Near-infrared flares from Sagittarius A star have been observed since the early 2000s. X-ray flares have been detected by NASA's Chandra X-ray Observatory. Radio flares are routinely seen. But the mid-infrared gap, the wavelengths between the near-infrared and radio, had never been directly sampled during a flare event. Until Webb, the flare lasted approximately 40 minutes and was detected at a wavelength of 8.1 microns. Simultaneously, the team was conducting radio observations using the submillimeter array in Hawaii, and they found something further, a radio counterpart to the mid-infrared flare, but delayed in time. The radio emission lagged behind the mid-infrared emission. This lag tells a story. In the magnetic reconnection model, electrons are accelerated to high energies first, producing the high-frequency, shorter wavelength emission. As those electrons cool, losing energy to synchrotron radiation, they drift toward lower frequency emission. The mid-infrared flare comes first. The radio flare follows. We are building an increasingly detailed picture of the processes that take place in the immediate vicinity of a supermassive black hole, said Witzel in a statement. The quality of our mid-infrared data is yet another testament to the James Webb Space Telescope's enormous technical capabilities. The MIRI detection was not just a new wavelength ticked off a list. It was the missing piece of a puzzle that theorists had been trying to solve for years. The mid-infrared lies at the transition point between where near-infrared models stopped and where radio models began. By bridging that gap, the April 2024 observation confirmed that the magnetic reconnection model is not just plausible, it is the mechanism. The flares across their full spectral range tell a single coherent story. The picture is becoming clearer, but it is also, in its newfound clarity, becoming stranger. Let's step back from the data for a moment and ask the larger question: why does any of this matter? Why should the fact that a black hole 26,000 light-years away is erupting 5 or 6 times a day change anything about our understanding of the universe? The answer operates on several levels. At the most fundamental level, Sagittarius A star is the only supermassive black hole we can study up close. M87 star, the black hole in the Messier 87 galaxy made famous by the first event Horizon Telescope image in 2019, is 55 million light-years away. Every other supermassive black hole in the universe is further still. Sagittarius A star, at 26,000 light-years, is our backyard neighbour by comparison. This means that any physical process we can detect in Sagittarius A star is detectable with an instrument precision that is simply not available elsewhere. The time delay of 3 to 40 seconds that Youssef Zadeh's team measured? At the distance of M87 star, the same event would be a fraction of a millisecond of phase difference in a light curve we could barely resolve. It would be invisible. Sagittarius, a star, is our laboratory for the extreme physics of black holes. And the lesson it is teaching us right now is that even the quietest, most ordinary, supermassive black holes are far more violent and complex than our models assumed. That lesson has a broader implication. Most large galaxies have a central, supermassive black hole. The Milky Way, at its current stage in cosmic history, is considered relatively quiescent. A black hole is not currently consuming material at anything like the rate it did in the distant past, when the galaxy was younger and denser. But even now, even in this period of cosmic retirement, Sagittarius A star is erupting hundreds of times a day. What was it doing when it was actively feeding billions of years ago? What were the black holes at the centers of the earliest galaxies doing when the universe was a few 100 million years old? We are beginning to suspect that the answer is far more than our models ever accounted for. The Webb observations of Sagittarius A star are reshaping how we think about black hole activity across cosmic history. And that has profound implications for everything from how galaxies form, to how elements are distributed through the universe, to how the environments around ancient stars may have influenced the development of planetary systems. In that light, the endless eruptions of a black hole 26,000 light-years away are not a local curiosity. They are a data point in the largest story there is. But the most immediate challenge is simpler. Build a model that actually fits what Webb saw. Because right now, no model does. The non-stop variability, the two distinct populations of flares, the random timing, the magnetic field strengths implied by the time delays, together, they strain the existing theoretical framework for low luminosity AGN. They are not impossible. They are not inexplicable. But they require refinement of theory that has not yet been done. Youssef Zadeh's team knows this. It is, in part, why the lead scientist has already proposed a follow-up observation, an uninterrupted 24-hour watch of Sagittarius A star with Webb. If approved, it would be the longest single continuous observation of the galactic center ever conducted. Twice the duration of any single epoch in the 2023 to 2024 campaign. If we can observe for 24 hours, then we can reduce the noise to see features that we were unable to see before. Youssef Zadeh said, "That would be amazing. We also can see if these flares show periodicity or if they are truly random." That last question matters enormously. If the flares are truly random, It means the triggering mechanism, whatever releases the magnetic reconnection event, is fundamentally stochastic. There is no clock, no cycle, no accumulation of stress that builds to a predictable threshold. The chaos is intrinsic. If a periodicity is found, even a buried, noisy one, it could point to something orbiting the black hole. A density wave in the accretion disk, a resonance between the disk and the black hole's spin, an orbiting compact object. There is a reason theoretical physicists want this answer badly. The spin of Sagittarius A star, its angular momentum, is, as Nobel laureate Reinhard Genzel has said, the last quantity we need to fully characterize it. Under general relativity, a black hole is completely described by just two numbers, its mass and its spin. The mass of Sagittarius A star is now known with remarkable precision. The spin is not. Detecting a periodicity in the flares could constrain it. 1 year of watching yielded revelations nobody anticipated. Imagine what 24 hours of unbroken observation might reveal. There is something quietly profound about the arc of this story. In 1928, an engineer at a phone company built a rotating antenna in a New Jersey field and stumbled onto a radio signal from the center of the galaxy. He did not know what it meant. The technology to understand it did not exist. In the 1990s, two teams of astronomers spent a decade photographing stars they could barely see against the blazing background of the galactic center, tracking their orbits by fractions of an arc-second per year. Doing the same math Kepler had done for planets and concluding that what the stars were orbiting was 4 million solar masses of nothing visible. In 2022, an Earth-spanning network of radio dishes, coordinated to nanosecond precision, assembled a blurry orange ring of light that told us it is there. We can see its shadow, and it is exactly what we thought it was. And now, in 2023 and 2024, a gold-plated mirror floating 1.5 million kilometers from Earth, cooled to 7 degrees above absolute zero, watched the accretion disk of that black hole erupt hundreds of times, in multiple wavelengths, simultaneously, and for the first time recorded the sound of energy leaving particles as they cool near an event horizon. A few seconds of delay between two colors of light. It sounds like almost nothing. It is in fact one of the most precisely constrained measurements ever made at an event horizon. And it encodes the magnetic field strength, the electron energy, the cooling timescale, the physical conditions in a region smaller than the distance from Earth to Mars. We have gone from Carl Jansky's merry-go-round to measuring the magnetic field of a black hole. In less than a century, the Milky Way has been orbiting this black hole for the entire history of our solar system. Every star that has ever existed in our galaxy has felt its gravity. Every atom in your body was forged in stars that lived and died in its gravitational shadow. It has been there the whole time, erupting, flickering, tidal waving its own accretion disk with magnetic fire 5 times a day. And for all of human history, we had no idea. We knew a thing was there. We knew it was massive. We could see its shadow. What we could not see until now was that it was alive. That it is always moving, always building, always releasing. That there is no stillness at the center of the Milky Way. There is only the fire. A study by Farhad Yousafzadeh and his collaborators, titled Nonstop Variability of SGR-AA, using JWST at 2.1 and 4.8 micron wavelengths, evidence for distinct populations of faint and bright variable emission, was published in the astrophysical journal Letters on February 18, 2025. The mid-infrared MIRI detection was published in the astrophysical journal Letters in January 2025, authored by Sebastiano von Fellenberg and collaborators at the Max Planck Institute for Radio Astronomy. The Webb observations discussed in this video were conducted under NASA's James Webb Space Telescope program, a collaboration between NASA, the European Space Agency, and the Canadian Space Agency, operated through the Space Telescope Science Institute. All flare statistics, timing data, magnetic field estimates, and researcher quotes referenced in this script are drawn directly from the published research and official statements from NASA, Northwestern University, and the Max Planck Institute for Radio Astronomy. The black hole at the center of our galaxy is, as of this writing, producing approximately 5 to 6 major flares per day. It was doing so while this video was made. It is doing so right now, as you watch it. We are, all of us, orbiting a fire